We're still in chapter 4, the performance evaluation metrics. The second part, this is the second part of chapter 4. We already talked about the communication overhead. Now we will talk about other evaluation metrics: the speed up, efficiency, scalability, and fault tolerance. Let's start with the speed up. We can name it also the acceleration, because it quantify the difference between the time when the program was sequential and the time when the program became parallel. Or we can say how much exactly the parallelization gave us gain compared to the sequential program. For example, the sequential program used to take 10 seconds. The parallel program now is taking 5 seconds. This is an acceleration of the program, and we will name it the speed up of the program. And it is quantified using this formula: the time with one processor over the time with P processor. It gives us a number between, of course, usually between 0 and 1, because it can give us any number. It can in fact give us a 1. 1 means that the time sequential is equal to the parallel time, and this means that the parallelization doesn't really give us anything new. It can give us a number greater than 1. Greater than 1 means that the time with one processor is greater than the time with many processors, and this is a good thing. This is what we want. The bad thing is when it gave us less than 1. This means that the time with one processor is better than the time with many processors, so the parallelization did a bad thing to our system. Let's take some numerical examples. If we have a program with one processor, 16 units of time. Let's say when the parallelization gave us 8, the speed up will be 2, because 16 over 8 will give us 2. That means the parallelization has doubled the execution speed, or halved the execution time. This is the same: half the execution time or double the execution speed. This is a good thing. A bad thing can happen when the parallel time is greater than the sequential time. Means that the speed up is less than 1, like this case. In this case, we say parallelization has reduced the execution speed, and this is a problem. In case when speed up equal 1 means that the sequential time is equal to the parallel time, the parallelization has had no impact on the execution speed, so we wasted our time in the parallelization process. Okay, let's talk about the speed up types now. According to the number of processor used, means according to the costs of resource allocated to our parallelization process, we can decide the speed up might be less than the number of processors. This is the normal case. The speed up can be equal to the number of processors. This is linear acceleration. Means that when we have the time sequential 16, the time with the time with two processors will be 8. 16 over 8 is 2. The speed up now is 2, and 2, the 2 of the speed up is equal to the number of processor used. This is a linear acceleration. Linear accelerations means that if we are using 16 in the we have 16 in the sequential, when we use T4 with 4 processors, we should find 4 here in the speed up. 4 here means also 4 here. 16 over 4 equal 4. Another example, 16 T8, we should find 8. So here we should find the time should be 2. 16 over 2 is 8. This is the linear acceleration. The normal case is that the speed up is less than the number of processors, less than linear. This is the normal case because we have many other constraints and overhead, etc. So adding more processors will not linearly speed up our program, but less than linear. Let's take a look at this curve. This is the linear curve. This is the number of processors. And this is the speed up. Linear means as much as you add processors, as much as you have speed up. The normal is as much as you add processors, you will gain time, yes, but less than linear. This is the normal case. There is two other cases, is super linear. When adding more processors, you will gain time more than the linear time. This is not normal case, this is super linear case. This doesn't happen actually, only if there are other things that contribute to the acceleration of the program other than just parallelization. حاجات اخرى عملناها في البروجرام يسرعوا في البروجرام، مش كان الباراليزيشن هي اللي قاعده تسرعنا في البروجرام، وقتها نتحصلوا على السوبر لينير. The last case is that the parallelization is slowing down our program. This happen in case like this, when we make a parallel program, like we are destroying our program. Generally, speed up cannot exceed the number of processors, so generally speed up cannot exceed the linear curve. In case of super linear like this, there must be additional source of time optimization beyond mere task parallelization. For example, the task management optimization, the placement and scheduling of tasks, the load balancing. حاجات هذوما يربحونا وقت أما not directly related to parallelization. The system level optimization, حاجات in the hardware that can optimize the time but not directly related to parallelization. The communication efficiency, reduced overhead, network latency. هذوما حاجات يخليونا نربحوا وقت بخلاف الباراليزيشن. كي نربحوا وقت بخلاف الباراليزيشن وقتها نجموا نفوتوا اللينير ونوليو نحكيو على سوبر لينير. Okay, this is the speed up. Let's talk about super linear speed up scenario 1. Here are some examples to illustrate the idea of super linearity. Let's say we have an algorithm for I from 1 to 100 we will initialize an array with zeros والarray هذا فيه 100 elements. Simple. This requires 300 instructions. Let's say 100 increment of I, 100 tests if I exceeds boundary. ديما باش نعملو comparison with 100 وصلنا ولا لا, and 100 assignments. So we have 300 instruction to do. Let's say we have a machine with 100 processor, then no need for a loop, and each processor can run the following algorithm. عندنا 100 processor, no need for a loop, كل processor باش يعمل 0 في cell معينة. In this case كل processor باش نعطيوه الانديس متاعو ونقولوا له يحط صفر في السيل اللي هو لاهي به. In this case the speed up will be speed up for 100 processor 300 متاع sequential time speed up متاع 1 وهذايا speed up متاع 100 processor. كل processor باش يعمل هذه and هذه, so كل processor will need 2 units of time. 2 units of time هي 2 اللي هي speed up متاع البروجرام when we have 100 processor. نلقاو 150 is greater than p, which is a super linear speed up. Here not only the parallelization gave us gain, but also the scheduling of tasks across multiple processors to minimize execution time. The superlinear speedup in this example suggests that the parallel execution time is less than what would be expected from simply dividing the serial execution time by the number of processors. This is an example when we sometimes find superlinear speedup. A second example can happen in a tree, search in tree, like this example. Let's say we have one processor and we will search for this item. Searching for this item require comparing the target, the search value with this item, then with this item, then with this, then with this. عادية يعني research في أربع عادية. So this is 8, 9, this is the 10th. So the time when we have one processor will be, let's say, 10 units of time. If we have two processors, each processor will deal with the half of the tree. In parallel, at the same time, processor P1 and processor P2 will look for this value. They will not find, they will both together look for this value. They will not find, they will look for this value. P2 will find the target in 3 units of time. So T with 2 processor equal 3. If we calculate the speed up here with 2 processors, we find that T1 على T2 equal 10 over 3 equal 3.3, which is greater than the 2. Again, the 2 is the number of processor. This is a super linear acceleration or speed up. The next metric is the efficiency. It measures the proportion of time for which processors are actively contributing to the computation. يعني الوقت اللي البروسيسورات يخدموا فيه. It is calculated as the speed up over the number of processors, and this metric is between 0 and 1. 1, when the efficiency is 1, means that it is 100, the system is 100 efficient, means that all the processors are doing calculations all the time. As much as the efficiency is getting down to 0, as much as the system is not really efficient and is wasting the resource of calculation. Let's take a numerical example. Suppose that we have 5 processors. The time with one processor is 8 seconds. The time with 5 processors is 2 seconds. Then we have the speed up 4 8 على 2, and the efficiency is 4 over 5, which is 0.8. This means that 80% of the processors are used. Another example, let's consider this algorithm for tasks like this, and then we have 3 processors. After some dependency analysis, we can see that T3 and T2 or T3 and T1 are dependent. Yes, this one. So T3 must be executed after T1. Okay, we put T3 after T1, and with 3 processors we have the efficiency 0.66. How did we find this? The sequential time is 4, the parallel time is 2, because this is 2, so the speed up is 2 over 3 is the number of processors, equals 0.66. So this is how we found the efficiency. If we have 2 processors, now look at this, the efficiency is 100% of the processors are used during the whole time. This is 100% efficient من point de vue بطبيعة البروسيسور. كان نحسبها هذايا نلقاو اللي الافشنسي هي speed up على number of processors. speed up هو 4 over 2 equal 2 و 2 على number processor 2 نلقاوها 1, which is 100% efficient. The fourth metric is scalability. It refers to the capacity to increase computing power when adding resources. We can add more resources to one single node. Adding more resources to one single node to make it stronger is a vertical scalability, while the horizontal scalability is when we add more nodes to the whole system in a distributed network to distribute the load more evenly across the infrastructure. So how to evaluate scalability? This is scalability in general. How to quantify it? It should be noted that the scalability has multiple perspectives. Scalability regarding what? It can be scalability regarding the communication overhead, or scalability regarding the speed up, efficiency, fault tolerance, load balancing, all other relevant metrics to assess how well a system performs and adapts when scaled. Yani when the system is getting bigger, what about the communication overhead? Is it getting bigger linearly, super linearly, or it's not even getting bigger? Let's quantify this. To quantify the scalability, we need to take one perspective. For example, let's take the perspective of the speed up and study the scalability of 2 parallel systems regarding the speed up. If we add more resource, what about the speed up? Let's take a numerical example regarding the time. We have a system A and a system B with one processor. System A 100 unit of time, system B 100 unit of time, but with 2 processors, the system A 60, the system B is 55. So we can notice that when we add more processors, the system A is getting better. More resources, system A is rapidly getting better, more rapid than the system B. Here we can say that the system A is better scalable than the system B regarding the speed up. We are counting, of course, the time. The speed up will يعني we were talking about time, but speed up we need to use the formula shown previously. Here this is the sequential time over the parallel time for two processors, for system A and for system B. We can see that for two processors speed up is 1.6, 4 processors 2, 8 processors 5, 16 processors 8. This is the way the speed up is getting bigger with the increase of the number of processors for system A. For system B, the increase of the number of processors give a different speed up increase rate, which is less than the system A. That's why we said that the system A is more scalable regarding speed up. We can compare this visually. We can plot these numbers here in a curve. This is the blue is the system A. This is the system A. You can see the scalability of the system A is better than the scalability of the system B. Means when we add more processors, this speed up is getting bigger, higher with the system A. Let's now move to the last metric, which is the fault tolerance. The fault tolerance refers to the ability of a parallel and distributed system to continue operating properly in the event of failure of some of their components. To quantify the fault tolerance, there are some metrics to assess the fault tolerance. Mean time to failure is the average of time a system operates before experiencing any failure. Higher mean time to failure indicates better reliability and fault tolerance. It will most probably not fail soon. There is another metric, mean time to repair after failing. How much time do we have to wait before repairing the system? Of course, here a lower mean time to repair contributes to higher system availability. قد ما يكون mean time to repair قصير معناها السيستم مش باش يقعد on pan برشا. Based on these two metrics, we can calculate the availability of the system to represent the fault tolerance as mean time to failure over mean time to failure plus mean time to repair. Let's take an example to understand this metric. Let's consider scenario 1 where the mean time to failure is 30,000 hours and the mean time to repair is 5 hours. Applying the formula give us 99.98% of availability because the mean time to failure is so high and the mean time to repair is so low, so this will give us a high availability, which indicates the high fault tolerance of the system. If we take another scenario where the mean time to failure is 500 hours compared to this is so low, every 500 hours we expect a failure, and this failure to be repaired we will need 50 hours to repair, while we needed 55 hours to repair in this scenario 1. This is a very bad system regarding fault tolerance, and if we numerically, if we calculate using these numbers, we can find that the availability of the system is 90%, which is so low. For the system to be reliable, we cannot work with a system that works 90% of the time. Ensuring high availability is indeed a key component in achieving a high fault tolerance in a system. And done.